The reaction of amide hydrolysis is a method for converting amides into carboxylic acids. And this can be done with, any number of different amides. But it's typically done under acidic conditions. And as a result of this reaction, we form a carboxylic acid plus an amine. And this reaction probably sees most of its common applications, some of its most important uses in the degradation of proteins. If you think about what a protein is, it's a series of amino acids strung together, and those amino acids are strung together with the peptide or amide bonds. And so if you want to break the proteins up, you're going to do that in this exact same way by cleaving this carbon-nitrogen bond and getting back your carboxylic acid and your amine. Mechanistically, this reaction has a lot of similarities to another reaction. It's extremely similar to the acid-catalyzed hydrolysis of esters. Really, one of the differences here is with acid-catalyzed hydrolysis of esters, we typically prefer to use base conditions, even though acidic conditions will also work. With amides, we almost always have to use acidic conditions because the use of basic conditions would require a leaving group of N-, and that's quite a bit worse than, say, OR- or hydroxide as a leaving group. So we almost always have to use acidic conditions. Now, as we said, the mechanism here is extremely similar to the hydrolysis of esters. And so what I'll do here is I'll put both of those mechanisms up so that we can see them side by side to see the similarities. So how do we start here? Well, in the case of the ester hydrolysis, by adding acid, we protonate the carbonyl. In this case, exactly the same first step. We protonate what is in this case the amide, but it's still the oxygen of the carbonyl that's being protonated here. From here, our nucleophile is water, and that can add in to this activated carbonyl. And again, that step works exactly the same in both mechanisms. We then get a transfer of a proton from the oxygen that just added in over to our leaving group. That gives us our our cation that's going to turn into a good leaving group. Sorry about that. The stylus is giving me a little bit of trouble here. And we just want that to be as clear as possible. But we can see it's the same intermediate for both reactions, just a different leaving group. At this point, one of the OHs adds in, kicks out our leaving group. Same thing in the ester hydrolysis. And in both cases, we're left with a protonated carboxylic acid, which then loses a hydrogen to give us the product. And so truly the only difference between these two reactions is that we have a different leaving group. But the mechanisms, the products, all exactly the same.